Hello students, in this session we will talk about the non-parametric analysis of variance that we use or apply when one of the underlying assumptions regarding analysis of variance is assume data to be approximately symmetrical or have the similar shapes. In that case, we cannot apply parametric analysis of variance. We go for non-parametric analysis of variance, and I have chosen the same question on which we have already applied or used one-way or parametric approach of one-way analysis of variance 15.34, in which we are given three data sets for three different policies or advertising policies being adopted in 18 stores randomly divided equally into three groups of six each. What I've done, I have already written down the null and alternative hypotheses that will not be different from the one we have stated in case of parametric one-way ANOVA. So there is no significant effect of advertising policies on mean sales would be your H0 and H1 would be there is a significant effect of advertising policies on mean sales. The level of significance again I have changed it to zero point 0.05. The test statistic that we follow in this case is H statistic that follows chi-square, and the structure is based upon the ranking of observation. This is what Rj squared divided by Nj factor represents the average of the squared ranks that we assign to each value of the data. And this is what the approach we usually follow in case of application of non-parametric test. So the computation is solely based upon the rankings of observations or data. That is why the formula is H equals 12 divided by n times n plus 1, then summation Rj squared over Nj minus 3 times n plus 1. N here represents the number of observations included in the data, that's 18. So now what we do, we define the critical region as I told you that this H statistic follows chi-square distribution. Therefore, chi-square distribution needs degrees of freedom. And since we are given three different levels of the variable that we are dealing with, that is advertising policies, therefore it gives us the degrees of freedom of 3 minus 1, that is 2. And we will use chi-square table to get the value of chi-square from that table. So this is the chi-square table. We go to zero point 0.05 significance level. This is the second column. 2 degree of freedom gives us 5.991 as the critical value of chi-square. So we state our rejection criterion as H0, the null hypothesis, will be rejected if chi-square calculated exceeds 5.991. Now in the second step, we go for computation, and I have copied a data set already. So we start giving ranks, and for this purpose, I'm changing the color of marker to red. And let me check the thickness of the marker. Yeah, that's fine. Now we start with the least value, and least value over here is 20. So we mark across this. There are two 20s. So what we do, we go for the average. This is what we do in case when the numbers are repeated. So if these two numbers were different, then we would have assigned these two values the ranks of 1 and 2. Since the two numbers are repeated, therefore we go for the average of the two values. So that's 1.5 and 1.5. And how do we get this 1.5? By taking the average of 1 and 2. So first two ranks have been utilized already. The next higher value is 21, and 21 is again repeated twice. So this one and this one. Again, we go for the average of the next two ranks, that is third and fourth. So the average of 3 and 4 is 3.5. So 3.5 and 3.5. This is how we assign the ranks to these two numbers. Then the next higher value is 22 in order, and there are three 22s, this one, and this one. And the ranks of these three should be 5, 6, and 7. So we go for the average of 5, 6, and 7. That gives us 6. So average is 6. We should assign to all these three values the rank of 6. Now, up to 7, we have utilized the ranks. The next higher value is there any 23? No, it's not there. So 24 is the next higher value after 22, and 24 is occurring here, this one, and this one. So there are two 24s available in the data. Now what we do, the ranks would be 8 and 9, and the average of 8 and 9 is 8.5. Now, the next higher rank should be 10, and 10 we should assign to the next higher value, which is 25. So 25 we need to count or observe how many times 25 is repeated. 25 is again repeated twice, and the average of 10 and 11 is 10.5. So 10.5 is the rank that we should assign to these two numbers. Then the next higher rank would be 12. Now 12 we assign to the next higher value, and the next higher value is 26. And how many times 26 is repeated? 3 times. So the next higher rank is 12. So 12, 13, and 14. So average of 12, 13, and 14 is 13. So 13, 13, and 13. Now the next higher rank should be 15. 15 we should assign to this one. The next higher rank is 16. We should assign to this one. Then we have 17. And then we have 18. Now what we do in the next step, we need to raise each rank, sum of the rank in fact. So we need to sum up the values of ranks. So total rank is 6 plus 1.5 plus 13 plus 3.5 plus 8.5 and then 6. The sum of the first column is 38.5. Then we go to the next column, 3.5 plus 10.5 plus 10.5 plus 1.5, then 6, and then 13. So the sum of the ranks of the second column is 45. We go to the third column, 16 plus 8.5 plus 17, 10 plus 18, 10 plus 13, and then 15. So 87.5 is the sum of the ranks of the third column. Now what we do to work out, as per the formula, so H statistic equals 12 divided by 18 times 18 plus 1. 18 represents the number of observations over here, and then 38.5 is the sum of the first column for the ranks divided by 6 because there are 6 values, then 45 squared again divided by 6, and then 87.5 squared divided by 6 minus 3 times 18 plus 1. Now we work out the inside the square bracket part first, and since the divisor is same, so we can first add the square of the ranks, sum of the ranks rather, add them all, and then divide in the end by 6. So 1860.583 is the value of this entire term, which is inside the square bracket. Then we multiply it by 12, then divide this answer by 18 times 19. That comes 65.2, and then we subtract from this answer 3 times 18 plus 1, that's 19. So 3 times 19 gives us 57, and 8.28 is the value of H statistic that follows chi-square. So we call it H statistic or chi-square calculated. So we can see if we compare it with the critical value of 5.991. So chi-square calculated value falls in the rejection region. Therefore, H naught is rejected. In conclusion, we write down as the test results are statistically significant at the 0.05 significance level, and data provide sufficient evidence to conclude that there is a significant effect of advertising policies on mean sales. So if we compare this finding with with the parametric analysis of variance that we have applied already on the same question, as the second step or as the next step we have applied over there or used over there Tucky multiple comparisons so that we can identify the pair of means responsible for the rejection of H naught. Over here we can't apply Tucky multiple comparisons, rather we have to look at the sum of the ranks that we have got for each column, and we need to consider whether there is a significant difference in terms of the average. So average, when we compare average squared, it is coming up for the first policy 247, then 337, 247, 337, and then if we compare it with 87.5 square divided by 6, that's 1276. So there is a significant difference if we compare the first two with the third one by one. So 38.5 compared with 87.5 is showing or reflecting the significant difference. Similarly, 45 versus 87.5 is also showing or reflecting the significant difference. But as far as 38.5 compared with 45 is concerned, we cannot consider this difference as significant or statistically significant. Therefore, we can say as compared to the previous case, our finding is same, and that finding is mu1 is nearly equal to mu2. Mu1 is significantly less than mu3, and mu2 is significantly less than mu3. So the same findings we have ended up with what we followed already in case of chi-square, in case of one-way parametric application of ANOVA. The next thing that I would like to focus on